Hello, everyone, and welcome to the final installment of our generalized Bayes chapter in this seminar series. Uh, a quick bit of housekeeping before we get going. Here are all of the usual links. Um, we have our workshop. We are still advertising. Registrations are still open, and we're looking forward to seeing everyone there very soon, actually. And also some advertising for another workshop. This one taking place in Bayescomp in Singapore this summer. Uh, there's the website. Have a wee look. As usual, we'll be using the Q&A during the talk, and Chris has been very nice and said that we can interrupt during. So if you have questions throughout, then we'll see if we can get to them. And so just to bring us back to what we've been doing this chapter, uh, we're now at the end where uh, Chris Holmes today is going to talk to us a bit about, uh, well, connecting generalized Bayes, which he's been really fundamental in developing, to Martingale Posteriors, which he's also been really fundamental in developing. So Chris is uh, Chris is a professor of biostatistics at Oxford and also now the director of AI at the new Ellison Institute. He may tell us a bit more about, as I said, he's been working a lot with generalized Bayes and also now these Martingale Posteriors uh, with a specific interest in statistical genetics, and I think he's going to try and bring that all together for us today. So I'll leave it now on to you, Chris.
Thank you. And yeah, thanks so much for the invite. Absolutely, yeah, delighted to be here. I'm just going to share my screen and just make sure that this comes through. Can you see this? Actually,
Perfect.
this sounds awful, but can you remind me how long do I have? How long should I speak for? Because I can.
You have until three local time.
Brilliant. Okay, thanks so much. So yeah, delighted to be here. I'm going to give quite a high level overview, and really it's a personal perspective, so it's highly subjective. And I just thought it was I thought it might be useful for you. It was certainly interesting for me to reflect on the connections between that took us from the paper on general Bayesian updating through to kind of martingale posteriors, and then I have a and back again. And I'll just hint at what the back again means at the end via the Bayesian Bootstrap. And I think the Bayesian Bootstrap is, as you'll see, is a remarkable, versatile, and interesting procedure and approach, which was fundamental to our thinking about a lot of these ideas. So yeah, I just to note, I have a joint appointment, or rather have separate appointments, both at the University of Oxford and the new Ellison Institute of Technology in the UK. So what I want to do is really tell a story of three papers, and sometimes they might be seen as separate, but they're highly connected. And so this is really this historical perspective of how they linked into one another and the kind of rationale behind them. And I just wanted to point that actually there are four papers, first of all, you would have seen, but three ideas, maybe kind of four fundamental papers. And in particular, all of these were developed with a colleague and close friend of mine, Stephen Walker, who was a really driving force behind this. And he's a professor at UT Austin. But also three amazing students that we had and now post student. So Pierre Giovanni Bisseri, who worked on the first paper with us on the general Bayes updated, Simon Lydon, who was a student at Oxford, is now working in industry, and Edwin, who is on this call, is here today, who's now, of course, a faculty member in Hong Kong. So I'm just going to talk you through really about how these three came about and the connections between them. So why don't we start with the first paper that talked about this or really develop this generalized Bayes approach in the context of an update. And that's the important thing, is that, and I'll flag that, the kind of mathematical equation existed beforehand, but we were very much coming at it from a Bayesian perspective. And I went to check my notes. I mean, this shows how shockingly delayed it was for us to actually get round to writing the thing. Is that Stephen and I first started discussing the idea about the general Bayes update, or this idea of replacing a likelihood function with what turned out to be a loss function, in 2009. So that's 7 years before the paper actually appeared. And it was in a Bayesian non-parametric workshop in Turin. And at the time, those BMP workshops had this really nice format. You had a workshop at the beginning for a week where there were lots of talks, and then a small number of people, I don't know, like 10 or 12 maybe, stayed on for a second week just to kind of bounce ideas off one another. And it's one of those great situations where you have a lot of time and space to think about things. And I can, although my memory might be kind of interjecting or putting in things which didn't actually exist, but in my memory, it was the following: is that Stephen came to talk to me about the following problem, or rather I was chatting to Stephen and he had this idea of this problem, and we got talking about it, and it was really exciting. And I think there was some kind of outing on the afternoon and we just missed it. We were just kind of deeply intrigued by this problem and trying to work it out. And to paraphrase what Stephen had posed was the following: suppose you have beliefs about a parameter. I'm really thinking about a statistic, a population level statistic that doesn't index a likelihood function, not necessarily. So it's not linked to a model. It's linked to a functional of a population. And you have information, data, that is relevant to learning about the parameter. If, and that is a question, if, you might say, in the absence of a model, there is no update. But suppose you are willing to entertain an update, then what are the necessary properties? What are the properties of that update that you would want outside of the likelihood prior construction? And so just in like simple notation, we have beliefs, which I'm specifying via a probability measure on the theta. That theta does not index necessarily a likelihood function. It's just a population statistic. You have some data that you think is relevant to learning about theta, and you want to go from a mapping from the augmented space back onto a probability measure. So it's an update, but I guess the key thing is it's not like in the traditional prior to data to posterior. We didn't think of it as that way. So maybe, you could think about it as these two things happening concurrently. I've got data and then I think about theta. So there's not that notion. It's just a general kind of mapping between two pieces of information, one which is a probability measure, one which is a datum or data, and a mapping back onto an updated probability measure. And so here's a concrete example, and a really useful one that I often think about is the median. Suppose you're just interested in the population median. Here I just said heights of children, or it could be anything really. And you're interested in statistical inference. Well, the first thing to note is that is a targeted question. So it's given you a purpose for the analysis. The reason why I'm undertaking this analysis is to learn about something, in this case, the median. Yeah. And that will become important. It was important. It's a really important part of the story behind the idea of general Bayesian or loss-based kind of Bayesian updating. So we have a target, and here I've denoted it theta naught. This is the unknown and never known. You're never going to know it, but you're trying to learn about it. And that's why we need statistics. Yeah, it's because you're never actually going to see theta naught. So you're going to have to estimate it or infer something about it. And we can write this as the minimization of an expectation, a functional of the true unknown population F naught and a loss function. And that loss function is, of course, is like an estimating equation or an estimator that targets the theta naught. Yeah. For the median case, for the case of estimating the median, then the absolute loss is an appropriate loss function that targets the population median. So this introduces the notion of an estimand, which is the theta naught, which is the object you're trying to estimate. And for those of you that work in medical statistics or biostatistics, this notion of an estimand has become really important. Okay, and it's important because it's now gained traction within the European Medicine Agency and FDA as well in the US. They'll talk about what is the estimand. So being very precise at the beginning of the analysis is what is the thing that you're interested in making statements about. Okay. So in this median case, you might have independent samples from some children. Say you've got 5 pieces of data. And you might have plausible beliefs on what that median of, I don't know, this particular age group of children might be. And the task is to combine those 2 pieces of information, one which comes as a prior distribution on the median, and the other one is the data themselves. So that's the task. It's really important to note that that's very different to how the Bayesian set up. And this was one of the kind of interesting points for us. And I put a quote in the top here, which is from a very famous and established, who I'm not going to tell you the name of, statistician, who essentially said, "You Bayesians are crazy." Yeah, because if you think about how you would solve the above problem from a Bayesian perspective, a traditional Bayesian perspective, is that the first thing you have to do is specify a full sampling distribution for the data. Yeah. So you have to put down a likelihood function, a model. And then you think about parameters of the model, and then you put your prior beliefs on those parameters. That wasn't the question. Yeah, I told you the question up here. We're trying to infer the population median. Yeah, that's a targeted question. Yeah, and so if you read Vapnik in his opening chapter of his statistical learning theory, talks about the problem with Bayes is it solves a more general problem. Yeah, you're asked a specific question, and you immediately jump to a more general solution, which is you first of all specify a model, a normalized likelihood function or a sampling distribution for the data, a generative model, which is indexed by parameters theta, which could be much higher dimensional than the target that you're interested in. And in fact, if you think about how you would solve the median question, it's not clear that. Oh, sorry, that's my phone going. I'll turn it off. Sorry. I'm just going to turn my phone off. So it's not even clear that you could parameterize the way you would parameterize the model would be through the median. Yeah, because that's not what Bayes tells you to do. Yeah. So you specify a prior in your model, and then you'd update it using Bayes' rule. And then you'd recover posterior beliefs on the estimand by first of all assuming that the model is true, to give you a kind of a mixture approach to what your model is telling you about the underlying population, and then you would solve for beliefs about the theta naught. So you've taken this very roundabout route to get to where you wanted to get to, which was inference about theta naught. So here's like point number 1, like historical point, or it's a pretty general point, which is one of the strengths and weaknesses of Bayesian analysis is that in Bayesian analysis, you separate out the modeling of the data from the task, from the inference task. Yeah, and the easiest way you think about it, if you study decision theory or decision analysis, which is essentially what you can think about is reporting beliefs, you can frame that as a decision task. In Bayesian analysis, you never consider formally, this is, of course, you always should as applied statisticians, but formally, you never consider the downstream task. Yeah, you model the data, you write down your best data generating process or your model for the data generating process. You then get some data that'll update your beliefs about the data generating process. And then given a model for the data generating process, you can answer any question. Essentially because, and just to go back up the slide, if you look at my cursor, because you have a model for the true underlying population. And from that, I can pick off any question. Any question you ask me about the population, I can just pick off. Yeah. And that's the way that Bayesian analysis works. And then if you then want to make a decision, that's a separate thing. You then put down a loss function or a risk function, and then you solve for maximum expected utility. Yeah. Now this is a strength. So this isn't so like Vapnik and others might say this is a weakness because you're not targeted. It's a strength because you can then ask any question you want. So you don't get one strength of Bayesian analysis, you don't get that idea of double dipping. Like, well, if I ask one question and I take an estimator and then I ask a secondary question based on the first question, it really mucks up all of your confidence intervals if you're non-Bayesian. Yeah, because you've then got a series of conditional statements and the confidence intervals are conditional on what happened before. Whereas in Bayes, because you separate out the modeling for the process from the decision, you're protected in that setting. But it's also a weakness, which is you might have really good beliefs about what the median of children of a certain height are. And you've now got to translate those beliefs about the parameter you care about into beliefs about the parameters of the model. So imagine you might have a really good prior on a statistic, the median, and then you've got to translate those into a prior belief on parameters of the model, such that if I look back on the marginal under the model, you get back the prior on the original beliefs that you had. That's non-trivial. There's a rather beautiful paper by Luke Bourne and Neil Shepherd in RSSB on this, which is around moment constraints in models. But it's a non-trivial to kind of translate that. And then secondly, as we've noted, that Bayes solves a more general problem. It does so in order to provide direct uncertainty on the value of the estimand. Okay, and again, I'm going to explain what I mean by this, but I have one of my say bugbears, one of the things that not say kind of frustrates me in the comparison of Bayesian inference with frequentist inference is they answer different questions. Yeah. So we might talk about the same estimand. We might both all be interested in say the population median. But Bayes puts a probability measure directly on the estimand, on the value of the unknown value of the estimand. Yeah, that's a huge strength. Yeah, rather than non-Bayesian is indirect. You want to make statements about uncertainty on the value of the estimand, and you do so indirectly through an estimator and finite sample variability of the estimator. That's an indirect measure of uncertainty. Yeah, Bayes is one way, and the extensions to Martingale Posteriors is a way of getting direct uncertainty. And I think that's a super important point to take away with you, is that you're putting a probability measure on the value, not indirectly via some finite sample variability of an estimator. So in general Bayes, in that paper by Bisseri, we were thinking about, should an update be possible in the absence of a likely? If we want to avoid the idea of a full sampling distribution for the data, but we've got good prior beliefs and we've got an estimator or a loss function, then should an update be possible? And if so, what does it look like? And it turns out, and this will give you a sense, I'm talking very high level throughout this presentation because, all the details are in the paper. But what was kind of remarkable in terms of the solution was the following, is that if you hold prior beliefs on the value of the target parameter and the data are independent, so then the notion is that the information has to be additive because you've got independent pieces of information. You've got some information which is data. You've got another piece of information which is a probability distribution on theta. You can think of it as a prior, but it's not like developed before you've seen the data. It could be developed alongside it. It's just a piece of information. Yeah. Then there's a unique solution for coherent updating in all situations. So we're asking, what is the property of the update, or what are properties of that update? And coherency in the update is one of them. And the easiest way to kind of illustrate this is, suppose you've got three pieces of information. You've got two datums, you've got y1, y2, two observations, and a probability distribution. Then for coherent updating, the sequential update, which takes the probability, let's call it the prior, and the y1, takes you to a posterior, and then takes that as the prior in the next step and combines it with y2, then you get an update to pi 1, 2. Yeah. Then this has to equal the joint update. So in other words, if I do an update on all three pieces of information simultaneously, so rather than putting them in a sequential order, then these two distributions, pi 1, 2 theta, has to equal this pi 1, 2 theta. That has to be, otherwise you're not coherent in the update. Yeah, actually, formally, there's a loss of sufficiency, which means if you do one update, yeah, then it's not capturing all the information, because if it's capturing all the information, I can just take that forward to the next update. In Bayes, the posterior distribution becomes the prior for the next update. And so it has to be equivalent, or should be equivalent. A property of an update means that you would want that to occur. And if you want to be coherent in the update, then there's a unique solution, which is shown to exist in the paper, which has the following form. And you can see the kind of log additivity of the information comes from this sum here. But it looks very similar to Bayes. But of course, it has the loss function replacing the log likelihood, or the negative log likelihood in here. Now, this loss function, like for the median, this would be absolute. It has arbitrary scaling. Yeah, in which case we've got a learning parameter. We can take this out, where alpha is a free parameter related to information in the data. So alpha kind of tells you how much information is in the data relative to information in the other piece of information here, which is, let's call it the prior. Yeah. So a couple of points about this update, outside the fact that it's the only one that provides you coherent updating in all situations, in all circumstances. Well, the first, it has exactly the same form as something called a Gibbs posterior, and actually, the names are kind of used interchangeably. So that is a Gibbs posterior, which was published 10 years before our publication, which was by Zhang. It's really worth reading that paper on the Gibbs posterior, because it arrives at the solution. It has the same solution, but from a very different perspective. So the Gibbs posterior is derived in an information theoretic setting as an upper bound on predictive risk. So first of all, it's related to prediction algorithms, like so algorithms that would take some covariate and predict an outcome. And it's under this thing that they looked at, I don't know if they still do, in Bayes, which is a form of a randomized algorithm. And the randomized algorithm, it looks Bayesian, but it's not. It basically, the way it kind of, or my interpretation, it says, well, if I have a distribution over theta, which is now models of a parameter, if I take a sample from that distribution, then I can look at the expected loss. Yeah. So here's the task. You take a sample from the distribution, and then I look at the loss from plugging in that model with those parameters and looking at the loss to the data. And the loss to the data is given by the usual, by here is the loss function. Well, in that case, an upper bound on the expected predictive risk is given by this equation, which again has this form of alpha, this kind of trade-off in terms of the loss. And that's kind of interesting because, well, first of all, just to note, this isn't how you would do Bayesian prediction. So in Bayesian prediction, you would integrate out the uncertainty on the model parameters to get a posterior predictive, which is a marginal predictive. This isn't, the Gibbs posterior doesn't use a marginal predictive. It has this situation where you draw a theta, predict with the model, look at the risk, draw another theta from the posterior, look at the risk, and as that. So it isn't a Bayesian prediction, but it is an interesting result, and it does give the same solution. The other thing which I kind of want to go on, in a sense, on the record of flagging is this really important insight which was provided by Kevin McConway that we didn't cite in Bissery. And I don't know why we didn't cite it. And that must have been an oversight for not citing it, because I remember reading the papers and I remember even getting hold of his thesis at UCL. So Kevin McConway's work was on something called Supra-Bayesian operations. So what is a Supra-Bayesian? It's not super, by the way. You sometimes see people like, all Bayesians are super. This is a Supra-Bayesian. So this is how you pool expert judgments. So if you've got 4 Bayesians in the room, they all have posterior beliefs. How should you combine Bayesian's beliefs? That's the supra part. And suppose they've all got independent pieces of information. It's kind of like meta-analysis for Bayesians. Yeah. Well, what McConway showed in his PhD thesis, and subsequently in a number of papers, well, he showed it in his thesis and then it appeared in a number of papers, is that if you want coherent pooling, then you have to do it on the logarithmic scale. So you have to do geometric averaging of experts. So the standard thing would say, oh, if I've got 5 experts, they've all got beliefs, you do like a mixture model. Oh, we take a weighted set of beliefs. I put, weight 1 on Jan's belief and weight 2 on Jeremiah's belief and weight 3 on Edwin's, and I just average them and I get like a mixture model. Well, what McConway showed is that if you do that, you won't get coherent update, which is if I update the expert's beliefs to a single belief and then I give it a new piece of information and update the pooled belief, I would want to arrive at the same position as if all the experts updated their belief based on the new piece of information. Yeah. And then I averaged or accumulated them. So sorry, just to be absolutely clear, this operation McConway looked at, but in the question where Y1 was somebody else's beliefs. Yeah. And so what he said is that for coherent updating, do you first update all the experts and then expose the updated to the new datum? Or you do it all in one go where each expert updates and then you pool. So do you pool before the update or do you update after the pooling? That shouldn't matter. And what he showed is that the only way you can get that result is through geometric averaging of beliefs. And that was a really interesting result for us. And we didn't cite it in the Bisseri paper, but I'm correcting that wrong now because we should have cited it because I know it was part of our reasoning. Okay. So then the question is how should we go about setting this learning parameter? We've got this free parameter now. And again, here's a really interesting aspect is that one of the advantages of Bayes is that if you define a joint probability distribution on parameters in the data, then the learning rate is fixed. Yeah. There is no learning rate. That's it just falls out of probability calculus. And moreover, the information processing is optimal. And there's a nice paper by Zellner on this fact that Bayesian inference is like a perfect information processing system. Yeah. Kind of related to this idea of posterior sufficiency, which says that if you're Bayesian and you're kind of evangelical Bayesian, let's say, or subjective Bayesian, then if you've got data in a prior and I get your posterior distribution on parameters, you can throw away the data. There's nothing left in that data after you've updated. Which means, but of course, you would never do that. That you should never do that because you might want to do things like model check-in and like residual analysis. But formally, we've got posterior sufficiency of the posterior. You've got sufficiency of the posterior, which means it contains all the information. There's no loss of information in that, and that's where it shows it's kind of optimal information processing. But of course, you have to define this joint distribution, and that's where non-Bayesians really have a hard time. And one of the things they really have a hard time about is viewing theta as a random variable. So it would say, no, theta isn't a random variable. It's fixed. It's just it's unknown, but it's a fixed parameter. It's the estimand. It's the value of the estimand. So there's nothing random about it. Which causes, part of the disagreement between how Bayesian and non-Bayesians approach inference. But if you want to use general Bayes, then of course you've got to fix this learning rate. And I understand that you had a talk previously on this, especially, and that's especially tricky if you're trying to estimate multiple parameters. Yeah, and I think that would flag to one of the things that reflecting on this construction is that it's really good. It's kind of, let's say, most useful for univariate targets. So when you've got a very low dimensional parameter, like a single parameter, when the target becomes multi-dimensional, then this idea of a learning rate, how much information in the data, how much is in the prior, becomes problematic or becomes harder to deal with. Although I'm aware that there's some really interesting solutions out there. Okay. So we were I think in the paper, we just plucked out a few ideas. We could, I don't know, look at the variance or look at some other aspects, but essentially it was left as an unknown as how we should set the learning rate. And I think we were looking at initially in areas like objective Bayes, because if you look at this this is important. If you look at that functional form, this is the information from the data. So what you're trying to do is to come up with a way of saying how much information about theta is contained purely in the data. And so I think we looked at objective Bayes measures because they have a similar type of question. Yeah, if we have no prior or flat prior or non-informative. But I don't. My memory is that it wasn't hugely successful when we looked there, because by definition, all of the objective Bayes things were using self-information loss, like negative log likelihoods, and we were trying to get away from the likelihood function. So it wasn't so surprising that we didn't find much there. But what we did get drawn into was a technique in Bayesian nonparametrics, which came under this paper called the Weighted Likelihood Bootstrap, which appeared as a red paper in RSSB in 1994. And it was a computational tool that was developed to approximate a Bayes posterior. Yeah. So this was an interesting thing, because the motivation for the paper was not about general Bayes. It wasn't about non-parametric Bayes even. It was about a computational tool, a numerical approach to approximate a Bayesian posterior. Yeah. And it didn't have a prior in it as well. And the original paper is highly cited, but if you read the discussion, it's a discussion paper in RSSB, it's really interesting because it received a lot of criticism. And part of the reason for that is that these Markov chain Monte Carlo methods were just emerging following, Gelfand and Smith and others. And so people said, well, why would you use this technique to approximate a Bayes when you can get things with guaranteed like approximation error, like MCMC? So the timeliness of this approach as a numerical solution, it was not kind of well suited, because like MCMC was emerging, and that seemed to give us general tools for being able to approximate integrals to arbitrary levels of precision. But we didn't care about that, because we weren't looking to approximate a Bayesian posterior. We were interested in how do we calibrate the information in the data. And this WLP-B was purely data driven, which was interesting. There was no prior in the weighted likelihood bootstrap. And it took the following form. So this is the paper by Newton and Raftery. You drew samples from the Bayesian bootstrap, these Dirichlet weights, and then you picked off the parameter of your model, your likelihood function. Sorry, so here all the thetas are indexing likelihood functions, because they were trying to approximate a Bayesian model, posterior distribution on a sampling, on a likelihood, parameters of a likelihood function. And you just minimize, you find the minimum loss, self-information loss, negative log likelihood, where this is a draw from the Bayesian bootstrap. So the method is prior free, as in there was no way, there was no mention of how you could even use a prior with it. So you couldn't use a prior, which was good for us in the general Bayes, because we wanted to isolate the information in the data. And it also had some really nice asymptotic properties. And so the kind of fairly simple next step for us was to say, well, you can replace the self-information loss in the Newton and Raftery approach with the general loss function. Yeah, and create something which we called the loss likelihood bootstrap. But essentially it's the same thing, but we've now got the loss function in here. And then if I can draw these samples, which are easy to do because they're parallelizable as well, I just draw the Dirichlet weights, minimize, or draw the Dirichlet weights, minimize the loss. Yeah, with this loss function. So it's a weighted loss function. We could then go back to the original task, which is how to set that alpha parameter by calibrating those two things. I've got an equation, alpha, the exponential minus alpha sum, and I've got a bag of samples, and I can do things like match the moments. And I can't remember, to be honest, I can't quite remember exactly how we matched the things, but it was a way of saying, if you give me a bag of samples that's used this Bayesian bootstrap, then we can match these two things, this equation with the bag of samples, and that will somehow capture the information. And that would seem to be us a kind of a nice workable solution. The interesting thing there was the following, is that we started off looking at the Bayesian bootstrap as a way to set the alpha hat, the learning rate. But we ended up getting much more interested in the Bayesian bootstrap itself, because it seemed to have these like rather remarkable properties. So by searching, and this is often the way in research, isn't it? You search for something to help you with this, and then you find something that you think, wow, like that looks like an interesting avenue in its own right. So we were looking at this, and some of the properties we found, which was this, it got criticized. Remember that the original, the weighted, sorry, that should be a B. The weighted likelihood bootstrap was criticized as an approximation to the Bayes model. But it turns out that it has lower predictive risk asymptotically than using the true mod, the actual model, if the actual model isn't true. Yeah, so let me just repeat that, is that suppose you have your Bayesian model, you put a prior on it, you're going to use it for prediction. And suppose I can tell you, I can give you perfect computation. I'll give you IID samples from the posterior, or you could just solve it numerically. So there's no problems in working numerically with this Bayesian model. If your model is misspecified, then working with your original model or working with this weighted likelihood bootstrap, the weighted likelihood bootstrap using your same likelihood function has lower asymptotic risk. So if you and I agree on a model, but you do full Bayes and I do this, I'm going to beat you predictively. That's quite a surprising result. It's based on this really interesting paper by Fushiki, again, which is appreciated in the Bayesian literature, that says actually bootstrapping does better than Bayes, posterior predictives. So if you just do bagging, from Bryman's bagging, where you just bootstrap the data, fit the model, bootstrap the data, fit the model, that does provably better in terms of predictive risk, in terms of like self-information loss, than the Bayes model. If the Bayes model is wrong, and all models are wrong, so you're never in M, you're always in M open, never in M closed, the model's never true. The other thing to note is that the form of this thing here, this exact same form, although the W's are written as unit exponentials, but the same, like the Dirichlet is just a normalized set of exponential ones, is used outside of Bayesian inference with no mention to the Bayesian bootstrap. It's used to derive confidence intervals on Z estimators and M estimators. And it's actually got much better properties than, not say much, but it's got interesting properties relative to Efron's bootstrap, requires fewer assumptions. So if you were doing lasso, if I want to get a confidence interval on the lasso, I can use this with unit exponentials, i.e. Dirichlet 111s, and the confidence intervals are valid. If I did Efron's bootstrap, they're not. And it's because of the smoothness properties in the functional, is that the weighted likelihood bootstrap, or as they call it, perturbing the minimand, has less assumptions. Whereas Efron's, you've got smoothness assumptions on the solution. And then also we just had, there's simple ways to incorporate the weighted likelihood bootstrap into prior data into there. So the Bayesian bootstrap was, people hadn't read the paper, but it wasn't really that well understood in a way. I mean, people know about it as the limiting distribution under a Dirichlet process with a base measure and a concentration parameter going to zero. But the actual connection, what's it doing feels a bit opaque. And the connections to Efron's bootstrap were unclear. And for us, and I think certainly now Edwin was now kind of part of the discussions at this point. Edwin had arrived in Oxford, and had come out to Texas to sit with Stephen and I and work on things. Was this idea that came from this Blackwell and McQueen Polya representation of the Dirichlet process? Yeah. Which is really key to understanding what is the Bayesian bootstrap doing. It looks like this weird thing where you have these perturbed weights, but it's actually doing something very intuitive. And the Polya representation of the Dirichlet process follows the following: is that you've got your empirical distribution function, which is a set of atomic weights at the values of the observations. And you first of all make a prediction from the empirical distribution function. Now, because the concentration parameter is zero, you get an exact tie. So your prediction of n plus 1 in the Bayesian from the Polya scheme is to draw one of those values at random, uniformly at random, but then add it into the pot. So now one of your datums now has weight 2. All the other datums have weight 1. And then you renormalize. And then you go again, and you go again. And so what you get is this reinforcement on these atoms. And if you go to the limit, the kind of rich get richer. The ones that are stacked, have more points stack up, are more likely to get a draw on the next one. You can show that you converge to the Dirichlet 111 in the limit. And then picking off the parameter of interest gives you the Bayesian bootstrap. So it's actually got the Bayesian bootstrap is this very natural kind of sequential prediction update. It predicts, but then it takes the prediction and puts it back in and then conditions on it and updates, and then predicts, takes the prediction point, puts it back into the pot and then updates to get the reinforcement. And if you look at the difference between the Bayesian bootstrap and Efron's bootstrap in kind of pseudocode in a way, it looks like this. And this, I think, is probably have this in the paper with Edwin, is that both the Bayesian bootstrap and Efron's bootstrap start off from the same point, which is really interesting. There's no prior. They both have exactly the same starting point, which is the empirical distribution function. The Bayesian bootstrap wants to draw B samples, and it does that by first of all sampling from the empirical distribution and then updating, which is what any good Bayesian would do. You would sample a datum, and then you update, you condition on it, and then you do it again, and you do it again, and you do it again. You go round and round and round until you end up, you do that to the limit, and then you calculate your statistic on this extended data set. Now, because these are all tied, you don't actually need to do that. We know that there will be weights on the original y's, which are exponential ones renormalized, Dirichlet 111s. And Efron's bootstrap does what a normal non-Bayesian would do, is you plug in a distribution and you just draw IID and you don't update. And you do that n times. That's the essential difference between the two. So that's it for the non-parametric approach. Well, what about the kind of Bayesian approach, the traditional Bayesian? Well, it turns out actually conventional Bayes has a really similar predictive representation, where the posterior uncertainty this is now standard Bayesian analysis, arises from the data that you don't have. This is the key insight, I think, in Edwin's paper, is that posterior uncertainty, when we present posterior uncertainty in Bayes models, all of it arises from data that you don't have. It's the missing data in the population that can be imputed through these one-step predictions. In the previous approach, in the Bayesian bootstrap, that uses the empirical distribution. Here, this would use the marginal posterior predictive. And the key connection from that is a paper by Doob on an application of the theory of martingales, which essentially shows that all Bayesian methods, one way of interpreting that result is that all Bayesian approaches could be interpreted. The uncertainty arising in the posterior flows from a prediction, a joint prediction on the missing data in the population. I'm just going to skip over this for purposes of time. But this is maybe kind of one of the most important slides in the talk, is that the really nice thing about this predictive viewpoint is it highlights the essential distinction between Bayes and non-Bayes. So if theta here, theta bracket is an estimator, we think about frequentist uncertainty that arises on any estimate. We think about what would the estimator give us if I was to repeat the experiment? If I had another set of data, what value of the estimate would I get? And then repeat it again and again and again. Then I get different estimates, and the uncertainty in the estimates would characterize my frequentist uncertainty. Well, Bayesian uncertainty looks at something kind of similar in a way. You've got the same estimator, but the uncertainty flows from the data that you don't have, where that data comes jointly from the underlying distribution. They both have the same target. They both have the same estimator. Yeah. Now, this is really interesting because this is just the same result. But what we see from here is that the frequentist uncertainty is indirect. If I look at the variability that comes through this, it's an indirect measure of the true value, the theta naught, because it's a finite sample variability of the estimator. But Bayes gives you direct uncertainty, because by going to the limit, we pick off the value, we put a probability measure directly on the value of the estimand. Yeah. They answer different questions. And this goes back to something I said right at the beginning, is that Bayes and frequentist, we answer different questions. Yeah, and I think that's really important. Bayes asks a harder question. Yeah, what's my uncertainty in the value of the estimand? Rather than indirectly, what's the finite sample variability of the estimator? And of course, the estimator targets the estimand, but it's an indirect measure of uncertainty. The other thing that comes in is the prior doesn't enter into this. If somebody says to me now, like, oh, big difference between Bayes and frequentist is that Bayes used the prior, I'd say that's a distraction. It's nothing to do with that. I mean, I'm overstating it, yeah. But essentially we can see it here. There's no prior here. That's not the main distinction between Bayes and non-Bayes, not at all. The main distinction is about what are we actually communicating uncertainty about. The Bayes task is much harder because you're trying to ask a statement about the value. It's a predictive statement about the value of the estimand directly. It's a harder statement to do, so you have to make. Now, a prior is super useful to get us here, but that's not the essential difference. How am I doing for time? Okay. So when you view it this way, it says the essential task in Bayesian inference is actually to get a joint predictive on the data that you don't have. And nothing is a priori in this statement. You condition on what you've got, and you've got to make a predictive statement. So this allows you to do model check-in, cross-validation. It comes at a price. You have to be really careful about data dip-in and how you construct that predictive if you're not going to use a likelihood prior. And that's a key development and contribution of Edwin's work in the paper, is about if we use exchangeability, or based on exchangeability, then we don't need to directly use this predictive. We can get the posterior through Bayes' rule, but we can weaken the conditions of exchangeability and still get inference. And that's a kind of a key highlight in this kind of notions of martingales that comes into Edwin's work. So the starting point of the analysis is conditional on the data you've got. You don't care about defining a prior on the data that's already been observed. And, you know, when you think about it, if someone says, oh, what do you do? I model data. Well, kind of, why'd you do that? You've got the data. It's like, you know, why, you know, you step back, and this is something that Stephen said, like, why would you model the data that you've got? Like, if you go out and speak to somebody in the street and you say, I've got some data, I'm modeling it, they'd say, well, why are you modeling it? You've got it. So it's like, model the data that you don't have. That's the key thing. It's the data that you don't have that's needed to answer the question. So model that. And what that means is prior knowledge or expert judgment goes into defining the predictive. And prior elicitation becomes predictive model evaluation. The search for objective priors becomes the search for kind of objective predictives. And that's a different kind of viewpoint. I'm going to skip through, for kind of time interest, through the kind of how you go, the engine behind this, which is something called predictive resampling. I'm sure you're going to hear talks on this coming in. Just one thing to claim is important is it's important to state that we're in no way claiming that martingale posteriors or things that are based on this forward prediction are better than the likelihood prior construction. They're just different and sometimes can be really useful. So the likelihood prior, traditional Bayes, we're not suggesting that somehow that goes away. It provides coherent updating, a shortcut to the posterior, but you have to define the prior and the likelihood. This predictive updating is more general because it allows you to use the data that you've got to define the predictive, but you have to be much more careful then. Just a final note on the story, and this is the going back to targeting, is just to flag a new paper. Really, it was driven by, it was really driven by Andrew Yu, a postdoc, and Edwin on this, which is what we had is that we started off with general Bayes, and then we looked at the Bayesian bootstrap as a way to calibrate the uncertainty. But the predictive nature of the bootstrap and the really interesting properties took us through into marginal posteriors. But again, one of the issues is that if you're interested on a specific value, a specific parameter, you have to be careful that any inductive bias, your choice for model in this might kind of affect your inference for the original question. And so maybe there are ways of actually then retargeting. How can you kind of fit the predictive, but then maybe go back and retarget? And that's this recent paper on posterior targeting or posterior corrections that Andrew and Edwin have with myself and Judith Rousseau. And I think that's a really interesting future direction in semi-parametric inference. So just to conclude, General Bayes relaxed the M-closed model framework that said we're working outside of a true model, allows for low dimensional targets, robust inference, gives you direct uncertainty on the estimand. Setting that learning rate was hard, and I know there's lots of really, really interesting approaches to it now. We looked at the Bayesian Bootstrap originally as a calibration tool, and then got really interested in the Bayesian Bootstrap in its own right. And that idea of the Blackwell and McQueen Polya own representation, which says the Bootstrap is this very natural predict, update. That's what it does. But with effectively the predictions are all reinforcement of data it's already seen. And then when you see that, and then the connection to Doob that says, well, actually Bayes, normal Bayes has exactly the same interpretation, predict, update, using the posterior prediction. That then led us to think, and Edwin in particular, to think about how do you weaken the assumptions that come and then build more general predictions that start with the data that you've got. I think a key thing that it highlights is that the frequentist uncertainty and Bayesian answer different questions, but it puts them on an equal footing and it doesn't involve a prior. That I'm convinced that is that prior is a distraction in terms of what's the difference between Bayes and non-Bayes. You need to be careful if you go outside of the likelihood and prior, because you can't just put down any prediction because it could drift, and that's the Martingale conditions. And I think the final work on posterior correction is interesting. Thank you. Thank you so much.
Thank you so much, Chris. I think we have some time for some questions. So I don't know if anybody wants to kick us off. Otherwise, I have my own selfish questions. Shall I get going? I was just wondering, so Chris, you mentioned this shift from objective priors to objective predictives, but I've not heard this term objective predictives necessarily before, and I may have missed it implicitly between the slides, but could you talk a touch more about that?
Yeah, I think it's probably just a bit of a throwaway comment, which is that in a sense they're objective because you've just got the data, that you condition on the data that you've got, and then you want to kind of you then want to make this joint prediction going forward. And you would want that to be kind of objective. So one thing you would want to avoid is by when you do forward predictions that somehow you introduce bias, but by conditioning on data that you don't have.
Yeah.
And so I think that's what I mean. And it's interesting. We've had a recent paper on the use of LLMs, which show that on large language models, if you do this prediction, they drift quite badly, and so you can show that they're far from objective. Yeah, but I used it loosely.
Okay, so it's not so much in the same way that these objective Bayesians will talk about a set of principles to define their priors. There's no shift from maximum entropy to martingales.
Yeah, I think it's a really interesting question, is about, what would be the principles for setting up joint predictive models?
Okay.
Yeah.
Well, thank you very much. Do we have any other questions from the rest of the audience? Yep, Jay.
Chris, thanks so much. This was really cool. Shame we only had an hour. I could have sat here for another hour. So maybe on a different time we'll go through those last few slides you had to skip. One thing I'm always wondering about with these predictive sampling procedures is, in my mind, and perhaps I'm ascribing motives that were never there, but in my mind, when I first read this work, my interpretation and also the origin for much of my enthusiasm for the work derived from the fact that I thought of it as a connecting bridge between all these simulation-based tools that we now have in machine learning. We have LLMs, we have diffusion models, we have all these enormous constructions out there. And I always looked at something like a Martingale Posterior or predictive resampling procedure as a way to dip into that. And some of the more recent work that you've done, and also some work that I've been involved with, like some very severe limitations how far you can actually do this because of inherent limitations to these simulation models. Do you see any way forward to bridge that, or do you think that bridge is fundamentally broken?
I think it's a really interesting question. So I think what we're seeing is that if you want to get the Bayes uncertainty, there's a shortcut through Bayes' rule. Yeah, and to do that, you just need a prior. And that's Dave Finetti's representation theorem. Dave Finetti like nailed this. And if you open like Bayesian theory by Bernardo and Smith, when I look back, like when I first read it, I think it's in like the opening lines of the chapter, is that all of Bayes is about a joint distribution, and that's it. And then I thought, well, it can't just be that. And so then you get sucked into this, oh no, it's about prior, but it's actually, that's it. It's as simple as that. It's about a joint. Now, the Dave Finetti representation theorem is such a genius, because it says I don't actually have to do this operation. I don't have to do this high dimensional integral, because if the data is exchangeable, I can write it as a mixture representation under an IID sample, which is, so people think of it as, oh, I've got a likelihood and a prior, but actually it's the other way. It's if the joint distribution is exchangeable, there is a likelihood prior representation. So, but to your question, if you're not going to use a likelihood prior representation, then the challenge is, how am I going to do that integral? Like, we do it by sequential imputation, generate a datum, feed it back in, generate another datum. I think it's an open research question. I think it's a really interesting research question, which is like, how can you tackle that kind of integral in a fast way? Like, you could do it through online learning methods, and in a fast way that doesn't introduce biases.
Any final questions? Yep, Edwin.
Hey Chris, I'm going to ask you a slightly harder question. So you've been on this path, right, from GenBase to kind of in between to Martingale Posteriors. Like, do you kind of have a small hint or guess as to what you think, the future of these kind of generalized post-Bayesian methods will be? Like, where are we going to go? Like, are we going to get completely sucked into the world of like AI, or do you think we're going to kind of make our way back to models? Like, where do you see kind of Bayes in like 10 years or 20 years, so to speak?
I think there's a really interesting thing which is implicit here in this construction, is that you have data y1 to little n, and then you just keep going in the sequence. But I think actually you should replace this capital Y for, like, what's the information that you would like to have. It's not necessarily the same data that you've got. Like in Bayes, I've got data and I have to write a predictive model for more data. That's not necessarily the thing that you actually want. I might have Y and I might want something different in order to answer the question. And so I think there's something interesting about there'll be an interesting aspect, especially in the context of how can we utilize, generative models in foundation models can generate us lots and lots of information, not necessarily the Ys, but can generate us other pieces of information. And so I think there'll be something for kind of very interesting around that. And then if you're going to use large scale AI generative models, it's around the bias reduction. So I would say, I think that looks to me like an interesting kind of extension or avenues is, thinking about the data that you've got, thinking about the information that you would like, but you don't have. It doesn't have to be the same form of the information you've got. You just need a way of generating. And that's much easier, by the way, than going in reverse, which is, I know what I want, and I'm going to write a model for, I have to write it. If I have to write the model in reverse, it's much harder. It's much easier to think about the data that I've got generating what I want, rather than thinking about what I want and then how does that relate to the data that I've got. You can write it down. It seems to be much easier to think in the generative sense rather than the inverse sense.
Okay, thanks.
Brilliant. Right. Well, I think that's probably all we have time for today, unfortunately. But thank you again so much, Chris, for taking the time to talk to us.
Yeah, it's been great. Yeah. Thank you so much.
Thank you.
Thanks a lot,
thank you to
Chris.
everyone else. That was our chapter 1. So we're now going to move on to chapter 2. Our next talk will be the introduction from Edwin. So stay tuned for more information on that.